Hello, I am Ahmad, and in this video we are going to talk about lap length in concrete structures. Lap length is very important when you have a cut or you need to extend the reinforcement in order to attach the other reinforcement, especially in column footing. So assume that we have a column connected to a footing. And here we have a construction joint. In this case, usually the footing is concreted in advance, and later on we have the column which will be installed later. So assume that you have some reinforcement as the concrete column reinforcement, which are installed after the foundation is cured and it's hardened. Now, in order to keep the consistency of the behavior of the column and the foundation, if the column is designed as a rigid connection to the footing, we need to ensure that the bending moment which needs to be transferred to the foundation is properly transferred. For this reason, we need to have some reinforcement anchored to the foundation, which we supported in the earlier example to calculate the anchorage length of reinforcement inside the foundation. For this reason, we need to have a certain length of the extended reinforcement through the foundation to have a sufficient length overlapping the reinforcement inside the column. This length is called lap length. So in Eurocode, the lap length is calculated according to the basic required anchorage length. Also, if you have a long element, for example, a beam, and then at some point, perhaps you have not a full length of the reinforcement you need. Usually reinforcements are with the length of 12 meters or 6 meters available. But if you cut it and use it for somewhere else, then you might have some part of it to be available and you want not to buy more reinforcement. In that case, you need to overlap some of them at some point. So assume that you have a reinforcement and it is extended up to this length, and then you need to add the other one from this side. To transmit the load properly from one element to the other one, we need to overlap these two reinforcements. And the overlapping length is called lap length. Especially in columns, if they are long enough, then you might need to overlap some bars at some point. If they are in one layer, you can cut all of them at one point, and then in one single cut, you can overlap the other bars. But it is possible also to cut, for example, 50% of them at a lap. We will go through that. Back to Eurocode, clause 8.7 is providing the information regarding the lap length, laps, and mechanical couplers. In general, forces are transmitted from one bar to another by lapping of bars with or without bends or hooks, welding, mechanical devices. 8.7.2 laps. The detailing of laps between bars shall be such that The transmission of the forces from one bar to the next is assured. Spalling of the concrete in the neighborhood of the joints does not occur. Large cracks which affect the performance of the structure do not occur. Number 2, laps between bars should normally be staggered and not located in areas of high moments forces because of plastic hinges. Exceptions are given in 4 below. At any section should normally be arranged symmetrically. If we are talking about columns, it's better to find out where we have less moment. For example, in the connection of a column to the beam, perhaps we have the maximum, or to the floor, we have maximum bending moment. In that places, it is recommended not to have the laps. Usually in columns, the laps are happening in the 1/3 of the column height between two floors in the middle. For the beams, on the other hand, as far as the maximum bending moment occurs in the middle of the beam, it is advised that the lap length is not happening at that point. Number 3, the same clause. The arrangement of the lapped bars should comply with the figure 8.7, and the description here is explanation of that graph. We will go through that. In the same clause number 4, when the provisions comply with 3, it means that you follow the regulation given in figure 8.7. The permissible percentage of lapped bars in tension may be 100%. It means that we can cut or we can have the lap at one section when or where the bars are all in one layer. Where the bars are in several layers, the percentage should be reduced to 50%. So we can have the maximum of 50% lap in one section. Bars in compression and secondary reinforcement may be lapped in one section. This is exceptional than clause number 4. Now let's go through the given figure 8.7. The description in number 3 is the same as figure here. For example, we can see that the force from one reinforcement is going to be transferred to the other one. So here the maximum gap between these two bars should be 50 millimeter and should be less than 4 times phi. For example, if we are overlapping T20, then it should be less than 50 millimeter and 80 millimeter, whichever is smaller. And also here we can see that if you have two adjacent bars to be lapped in one section, then the distance between these two bars that are going to be lapped should be greater than 20 millimeter and 2 times phi. If we are talking about E20, the distance between these two should be 40 millimeter. And also the distance between two bars in the lap should be greater than 30% of L0. L0 is the lap length. In clause 8.7.3, the lap length is explained how to calculate it. L0 is alpha 1, 2, 3, 5, 6 times LB required, and it should be greater than L0 minimum. LB required has been covered in the other videos, and we had also 2 examples for that. Alpha 1, 2, 3, 5 also have been covered in the other videos. The only new thing here is alpha 6, which needs to be calculated. For example, in some national annexes like Finnish national annex, we can see that if you use alpha 6 to be 2, then you can assume that all the requirements in this figure 8.7 is fulfilled. Surely you can use alpha 6 other than 2, but typically I have seen that in many companies the value of 2 is applied for alpha 6. So it means that alpha 1, 2, 3, 5 is 1 and alpha 6 is taken as 2. Then 2 times LB required is L0 or the lap length. L0 minimum is 30% of alpha 6 times LV required, 15 times phi, and 200 millimeter. For alpha 3 also, we have a little bit different calculation compared to alpha 3 from the other videos. Usually I take it as 1. And for alpha 6, it is rho 1 divided by 25 power by 0.5, but not exceeding 1.4 nor less than 1. So it should be something between 1 and 1.5. As I mentioned, for example, in Finnish National Annex, if you use alpha 6 equals to 2 for tension reinforcement, then you can assume that the requirement is fulfilled. Rho 1 is the percentage of reinforcement lapped within 65% of L0 from the center of the lap length considered. It is illustrated in figure 8.8, and also the table is providing value of alpha 6. In table 8.3, values of the coefficient alpha 6, if you are lapping less than 25%, then you can take alpha 6 as 1. If it's 33%, then 1.15, 50%, 1.4, and over 50%, 1.5. You can also calculate the intermediate values by interpolation, but we have already the equation rho 1 divided by 25 powered by 0.5. But the explanation of 65% of L0 here, for example, assume that we are talking about this section considered, point A. It is from the center of the bar that is going to be lapped. For example, we are talking about bar 1, which is with the letter of B. From the center of this lap, we have L0 in both sides. So half to the right, half to the left, L0. And from this center point, you can calculate 65% L0 to both sides. So if we look at the bar C, which is cut at some point somewhere else, this is one bar. And here is the lap of bar C. I can write down that from here to here, this is lap of bar C. And the center line is here. So the center line of lap C is outside of our section considered. So here we can see that section is considered between these two dashed lines, and it is out of that. Also, if we look at bar D, we can see that bar D is lapped. The center of this lap bar of D, again, it's outside of the considered section. But if we look at bar E, where it is lapped, the center of this lap is inside the section of considered. So in this case, B and E are within the lap, and C and D are outside the lap. If all bars are with the same diameter, we can see that 2 out of 4 is going to be lapped, which is 50%. Now we can say that alpha 6 is, according to the equation, 50% divided by 25 powered by 0.5. It's 2 square root, and it is 1.4. And here we can see that for 50%, the value of 1.4 is given. If you have more laps, then you need to consider alpha 6 a greater value. Also, for example, if you are designing in Finland, then you can check the Finnish National Annex for the calculation. And here for lap length, we have this statement. When using a value of 2 for the factor alpha 6, it may be considered that the requirement in clause 872 part 3 for the longitudinal distance of the lap slice is met, and the bars may be lapped at the same cross-section pursuant to clause 8724. When calculating the lap length of bars in compression, a value of 1 may be adopted for factor alpha 6. I used, for example, this statement for one third party in my reports earlier in one project. And as far as the reinforcement was in compression, so we accepted to take alpha 6 as 1. Also, you can check the other statements for Eurocode for the lap length and also the transverse reinforcement. I put the clauses here that you can check. It is advised to check these and find out how to have the transverse reinforcement in the lap zone. Now let's have one example. In the previous video, we went through a foundation reinforcement to be anchored inside a foundation. And now here, as far as you are going to have this reinforcement to be anchored inside the concrete, most likely the reinforcement has been designed for the bending moment, and the column is assumed to be rigidly connected to the foundation. As a result, the reinforcement would be under tension or compression. As far as the bending moment usually on the column can be in both directions. For example, assume that it's coming from the wind mainly, and then the wind can blow from both sides. As a result, the reinforcement can be either in tension or compression. As far as for tension, we need a longer lap, so it is conservative if we design the lap length according to the tension. So L0 in this case needs to be alpha 1, alpha 2, alpha 3, alpha 5, alpha 6, and then L be required, and it should be greater than L0 minimum. We can assume that alpha 1, 2, 3, and 5 are all 1, and the only thing is alpha 6 to be calculated. So alpha 6 can be taken as 1.5 if you check the reinforcement distance between the lapped reinforcement is complied with the given regulation in figure 8.7. You have to check, for example, that all bars are quite close to each other, and the reinforcement which is going to be cut, they are not closer than 2 times phi and 20 millimeter. So if you don't want to check these detailing, that you can easily assume that alpha 6 equals to 2, and we calculated LB required was, so it was 850 millimeter. As a result, L0 should be 1700 millimeter, and it should be greater than L0 minimum, which is the maximum of 0.3 alpha 6 LB required, 15 times phi, and 200 millimeter. 15 times phi is, it was T25, so 15 times 25 is 375. And 200 millimeters, 0.3 times 2 times 850 is 510. As a result, L0 can be accepted to be 1700 millimeter. So it means that you need to have 1.7 meters for the lap. For sure, if you want, you can check the figure 8.7 and check if the distances between the reinforcement is quite fine. and then you can assume that alpha 6 can be 1.5. In that case, you can decrease 25% of this 1.7. So it will be about 1.275, or let's say 1300 millimeter. That is how we calculate the lap length. It doesn't matter if it is a beam, if it is a column, if it is a footing. So we need just to check what is the required length and then multiply the relevant factors and coefficients and find out what is the required length, or the L0. That's the end of this example. We went through the lap length explanation and how to calculate the lap length for the bars that might be cut at some point. It can be in a construction joint or in a line beam or in a line column, that you do not have the total length of reinforcement for one element. As a result, at some point you might need to cut the reinforcement and add the other reinforcement. So in this case, you need to overlap two reinforcement with a sufficient length to ensure that the force is transmitted from one bar to the other bar. Thank you for watching. See you next time. Bye.